Good evening, everyone. My name is Tyler, and tonight we're going to be talking about the physics within electric guitars. More specifically, we're going to see some of the concepts that we've learned in the past 3.5 weeks in PC 242, or Physics 2 in action. The main idea here is that we're going to focus on how exactly are these amazing instruments able to produce sound. We will be focusing quite a bit on the electromagnetic mechanisms found in the pickups, as well as examining some basic guitar circuitry. Alright, so without further ado, let's get started. So, let's start off very simple and broad here with the guitars. We see here that we have an acoustic and an electric guitar. Now, I'm sure we've all wondered what exactly are the differences between the two. Right? Well, let's look at the similarities first. Hopefully you're realizing that there actually aren't that many. Let's see here, you play them the same by using the fretboard for pitches, while perhaps using the same strumming patterns, and I think they're shaped pretty similarly in the visual aspect, and that's about it. Now let's talk about the differences. Right. I mean, I want to note first here that right now I'm simply laying down these simple differences first, so that hopefully when we get into the physics later on, we'll start to see exactly why things are the way they are. And what's really important here to first focus on is the way sound is produced. Right? After all, these are musical instruments, and let's see here, the acoustic guitar relies on vibrations from the strings, which resonates throughout this whole body over here, which ultimately produces sound from this hole over here. Hence, this is why the acoustic guitars are called hollow body, right? There's hollowness inside, and you can kind of think of this hole as a little mini amplifier, I would say, attached to the guitar. That's how I like to think about it. Now, electric guitars, on the other hand, have a solid body, right? We don't see any holes here, right? That means it doesn't really depend on the same technology that the acoustic guitar uses to create sound. So let's dig a little bit further into what are the differences here, right, in the electric guitar. So I want to focus on the choice of strings first. Okay, so we see that one of the key differences is that they use different strings. And if we see down here, the electric guitars actually have to, they require very specific metals that would be used in making the strings, and without them it just wouldn't work, right? And the reason why is because of their magnetic properties from these metals. And again, we're going to start off really slow, so I apologize if it's too slow, but for now that's all we have to know. We'll soon see why this is the case, but for now just know that electric guitars require metallic strings, specific metallic strings, for them to work. And if they aren't, for example, if you were to use an acoustic guitar string on an electric guitar, it simply would not work. However, if you do use an electric guitar string on acoustic guitar, though, it still would kind of function, simply because the technology isn't exactly not reliant on the strings themselves. It's more about the hollow body again. So, but yeah, anyways, for now, that's all we have to know. Okay, now that we've talked about the strings, let's get started with diving a little deeper now and start talking about some physics, right? So the main difference that we really see between an electric guitar and acoustic guitar are these little things right here, right? They're called pickups, and for now, we can think of them as what their name implies. They pick up vibrations, and then which come from the strings, and then convert them into electricity, which then goes out of your amplifier, and everyone goes rock and roll, right? So if it helps, we can think of them as transformers of energy, right? We're transforming vibrational energy, again, which are produced by the strings, into electrical energy, which you can then send as currents down into the amplifiers, right? However, the reason why we're here tonight though is to really see why and how this is possible. And to do that, we really need to first take a closer, an even closer look at these little amazing devices. Alright, so here is the pickup just by itself when removed from the guitar to give you a better view. If this seems really complicated, don't worry at all. I was able to find this lovely diagram online which really showcases each key component really well. And more specifically, what's even better is that we really only have to care about two key components here, which are these magnets over here as well as this copper coil. So each magnet here is supposed to correspond to each string, right? So because there are 6 strings in the guitar, as you can see there are 6 magnets here. And if you were to put this in the perspective of putting this pickup on the guitar, the strings would be aligned with each magnet. So again, coming back over here, you can see that these are the magnets and each string is right above it. There's also an alternative design where it's also pretty popular for them to use, instead of individual magnets, they would use a general just chunk, like a giant piece, a single piece of magnet that would go on here, and it would perform the same as well. But for the sake of this presentation, I think we're just going to focus on this particular model over here by this design. Now let's take a look at the copper wire over here, and believe it or not, this is actually just one wire. However, it's just wrapped a lot of times and I mean a lot. You can expect up to at least 7,000 turns, and they're really thin as well, thinner than like a human hair. So just wrapped a lot. And then over down here we have some bass play and then winding. These are just more for engineering purposes, and we don't really need to care about these for now, for the sake of this presentation. But anyways, we can think of these pickups as a group of, again, magnets that are being wrapped thousands and thousands of times by these copper coils, and we're going to see very soon on why they're constructed the way they are. And this is going to come after we review some physics and math to get some basic principles down. But for now, hopefully this gives you a very nice visual representation of what a pickup is, and definitely remember it for later because it's gonna be really important when it comes up again. Okay, so we're finally going to start talking about some physics here, right? So this right here is the fundamental principle behind how electric guitars work. It is Michael Faraday's law of induction. So let's review for a bit. The law basically states that when there is a magnetic field, there will also be a magnetic flux, and when the magnetic flux changes over time, it will result in an induced voltage, or as you can see over here, it can also be known as an EMF or electromotive force. We can see that the equation is negative N, which is the number of loops of wire, times the change in magnetic flux over time. Or you can think of it as a derivative in respect to time, right? dt. And to review again on the definition of magnetic flux, it is the strength of the magnetic field times the area of the surface, and then multiplying that by cosine of the angle between the magnetic field lines and the normal or the perpendicular line to the area. And this integral definition over here, we can also think of that as a sum of all the magnetic field line passing through an infinitesimal area element by the name of dA. Right? So whichever helps you visualize it better, feel free to do that. And one more thing to note here is this little negative sign over here. That's just a reminder of Lenz's law, which states that the induced current is going to oppose the change in magnetic flux. And we're talking about direction here, right? So the overall idea, what you want to take away from this is that changes in magnetic flux, again, over time, this is very important, over time will produce basically electricity or an induced voltage, okay? Alright, welcome to our little whiteboard, everyone. I apologize if the framing and quality isn't the best, as I'm using my phone for this, so I apologize if this is not Khan Academy level. But anyways, so now that we've talked about the basic constructions of a pickup as well as Faraday's Law, we can finally put these pieces together to see how everything works, right? So let me just write down Faraday's Law real quick to kind of just remind us, right? So EMF is equal to negative N over a change in flux over a change in time, right? So there to remind us. Okay, so let's start with drawing one of the magnets from the pickups. Okay, so it's gonna look something like, I'm gonna draw it sideways. Okay, so kind of like that. Is that okay? Yeah. Ooh, sorry about that. All right, so that's the magnet. Again, remember the pickup is composed of magnets, so that's one. This is just one of them. Okay, and as we remember, there are lots and lots of coils, right, from that copper wire. It's lots and lots of coil. You can see that from there. Okay, and since this is a magnet, it's going to have a north and south pole, right, like all magnets do. And we also know that because it is a magnet, it will also produce a magnetic field that we learned from class that's going to look like this, right? Just some lines that we can see here, right? Like that. It's going to be kind of in this direction, right? Because the north's going to want to attract the south, like that. Okay, so that's the magnetic field, and that's the magnet. All right, so now let's draw a string, right? So if you remember again from the pickup construction, the string is right here, right? It's very close. It's very close to the magnets, right? It's right next to it. And what's important here is that because they are so close, right, due to the close distance of the string to the magnet is actually going to induce a north and south pole on the string, along with its own magnetic field. So sorry about that. This is going to be south and north, right, because the south is going to want to attract north, and it's going to have kind of like a magnetic field kind of like surrounding it, like that. Okay, sorry if the drawing is not good, I apologize. But anyways, so what happens when we pluck a string, right? If we not pluck, sorry, if we, yeah, I guess it's pluck. Anyways, if we pluck a string, well, it's gonna cause this sudden motion of up and then down, right? Because the string is gonna like right? So we're gonna have kind of like this up and down motion, and soon we're gonna see that it's actually an oscillation, right? And what's important here is that the magnetic flux of the magnet, right, is going to be changed due to this oscillation, because there's an interference, right? It's going to be this constant oscillation is going to cause a change in flux. Okay, so now let's go back to Faraday's equation here, okay, Faraday's law, and we can start filling in some variables. Okay, so the N over here we know is the number of wires, number of loops, and we know that it's just going to be whatever the loop number is for this magnet. And we also know that this part is representing a change in flux over a change in time, which is happening over here, right? This oscillation is changing the magnetic flux of the magnet, and we know what's going to happen is that because of the change in flux, we're going to have an induced voltage, and hence an EMF, right? And that is where the voltage is coming from for an electric guitar. It is the change in flux due to the vibrations from the oscillation from the string that affects the magnet's flux. And again, this is only one magnet, by the way, so we're gonna have 5 other ones, and they're all gonna be doing the same thing depending on what string you play. But let me see. So the oscillation is going to change, cause a change in flux which we know now will induce a voltage. And again, since this is an oscillation, we know that the voltage isn't going to be constant, right? Because it's going up and down, right? It changes with time, right? The change in flux at one time is not going to be the same in another. And in fact, we can graph this as a graph. So let me just move this over here. If we were to graph it like this, draw a little axis here, whoops. And this is, V induced voltage, and then this is just time. We're gonna get a graph like this. It's gonna be up and down for the graph too, right? And we're gonna get a nice sine curve like that. Oops, there we go. Right, because it's gonna go up and down, right? And we know what's really interesting here is that, let's say this is a period, right? This is an oscillation period, T. We know that the frequency of the voltage induced is going to be 1 T, right? This is equal to F. And what's really cool here is that the frequency of the voltage is going to be directly the same as the frequency at which the string is bouncing up and down, which is quite fascinating, if I would say. Okay, so hopefully that gives you a nice overview about how voltage is generated through the change in flux over here. And I want to take a second and kind of take a step back to one of the earlier slides about the electric guitar strings, right? Remember how we talked about that the string can only be made out of certain materials for electric guitars to work, right? Well, now we know why, because only materials which we call ferromagnetic material, only these materials can have these induced poles, right? Over here by the magnet. So if you use acoustic strings, this whole process will not occur, right? You won't have this pole, you won't have this magnetic field, and you won't have this flux change when you plug it, right? And that is why the strings are very important when it comes to electric guitar, right? You have to get, strings made for electric guitar, not just any random guitar string you can find, right? Yeah, so hopefully that clears up a lot, and let's move on. Alright, so before we go on, I just want to show you some examples that I found online. This is by one of the professors on YouTube, and this is a really nice animation of what is actually happening from what we just talked about, right? This is the motion of the oscillation. This is the string right here. As you can see, these poles are attracting to each other, and they're creating these magnetic fields, and because of the change in flux, as you can see, due to this kind of interference patterns, the current is going to be generated. A voltage is going to be generated, which will pass the current down through these wires. And hopefully this gives you a better visual representation of what is happening. So if you're looking for a more real-life example, I think Discovery did a great job with their demonstration. So the green thing is the pickup, and it shows with this kind of blue shield of the magnetic field generated by it. And when they strum it, it demonstrates really well about how the oscillations that are occurring and how the change in magnetic flux, right? It's different at each spot depending on the time. And I think they also did a really good job on showcasing kind of like the sine curve and how the voltage induced is not constant, right? It varies with time. And hopefully that's another way to look at it, and that was a little bit less microscopic of demonstration, so I thought it was a great way to kind of wrap up the ideas that we talked about, and hopefully now you have a great idea of how voltage is generated in an electric guitar. Alright, welcome back. So the pickups that we've talked about so far have been single coil pickups, right? Well, what people have found out is that when you wind a magnet with a copper wire, like we've seen, it actually turns out to be a pretty great antenna. Okay, so our pickups are pretty good at being antennas, and this means that they're quite sensitive to electromagnetic interferences from sources other than just guitar strings. And what ends up happening is that these interferences cause an annoying humming sound that people don't like very much. Well, at least I certainly do not like it. And these interferences that I'm talking about here can be from electric and magnetic fields oscillating at specifically 60 hertz, which are generated from AC currents in a building's power wiring system. The hums can also radiate from lighting circuits and fluorescent lights. So before we move on, let's actually take a real quick look at an example in case you don't know what I'm talking about. Hey everyone, so this is my Stratocaster, very lovely, and it sounds like this. Pretty nice, huh? Well, that's what the strings do. Now let's see what other objects do though. So let's take anything with a circuit inside, so a mouse for example, and then just see what happens and how it kind of interacts with these pickups. So right, so hopefully that was pretty apparent about the humming noises, so it's real. And you might be wondering, why does the middle pickup produce extra hum compared to the other ones, right? Well, that's just because my pickup switch right now is set to the middle one. So if I was to turn it all the way up to just this neck pickup, we'll see the same effect again. And then the same thing with the one over here. Yep, so pretty cool, right? That's the humming noise that we were talking about. And now let's move on to talk about exactly what we can do to kind of combat this issue, which is pretty fascinating. So see you there. Okay, so the solution to this humming noise is called a humbucker pickup. Okay, there we go. And it looks pretty much identical to the ones we've seen, except for now there are 2 coils compared to 1. And you can see here that it's basically 2 pickups being combined into one, and we're going to talk a lot more about exactly how they're being combined. And in addition to canceling out hum, guitars with these kind of pickups are going to generate sounds that are a lot louder and bigger, and we'll also see why in just a bit. Okay, and before we dive into the physics, we should review a little bit about wave interferences. Specifically, we're talking about constructive and destructive interference. Okay, these should sound pretty familiar from class. Basically, a constructive interference would be when you're colliding 2 waves together. The resultant wave would be the sum of the amplitudes, right? So let's say this amplitude was 5 and this one was 5 as well. The resultant one would be 10. And same thing with the negative directions, right? It would be like a sum. Whereas destructive, on the other hand, the resultant wave is actually going to be 0, like a flat line, because due to the phasing, which causes when you add these together, they're going to cancel each other out, assuming that they're in the same amplitude. So let's say this is 5 again, and this is -5 this time. When you add them, you will get a 0, and same thing with all the other points. Right? And these are the 2 main ideas that we're willing to get a grasp here. And why is this important, you might ask? Well, it's this and the idea of phasing that really sits behind the principles of humbucker pickups. So it's really important to first get familiar with these before we move on. Okay, so now let's move on to see what exactly is causing this cancellation. What we need to first know here is that the reason why hum is even produced is because electromagnetic interference is independent of the magnet. And what this means is that the copper wire itself is the antenna, okay? And the magnet has no relationship to why the copper is like that. It's not because of the magnet, and the magnet is honestly only there to mostly interact with the strings. Okay, so if we were to graph the string signal picked up when we pluck along with the hum noises, this is what it would look like, right? Makes sense. So based on our knowledge in wave interferences, such as constructive and destructive, right? If we were to wound a second coil, but this time in the opposite direction, the hum would get canceled out, right? Because they would get destructive, right? Well, yes, but not quite. And let's see why. So here we see that this is what the two coils would look like if they're connected in opposite directions. This will be the first one, and this is the second one. The blue arrows are the magnetic fields, and these are the generated currents. And this is how they're connected, right? From negative to negative. That's the opposite direction. And the problem here is that, yes, even though hums will now get canceled out, the two pickups are out of phase, right? They're not in phase anymore. And we don't want that, since the whole point of this is to still preserve the guitar sound, but we just don't want the humming sound, right? Because if you see these electric field lines over here, what's eventually going to happen is that they're both flowing kind of towards each other, and if you follow my mouse over here, what's going to happen is a destructive interference that's going to happen, right? We don't want this for a signal. We want to preserve our signal. So let's really think about what we can do to change kind of this direction of these of electricity over here. So if you remember, the direction of this current is actually dependent on the direction of the magnetic field line, right? So if we kind of think back a little bit to the right-hand rule and how Lenz's law states that the induced current's direction will always oppose the change of the flux, right? And again, we have to remember right here that there is an oscillation going on, right? This is only just one moment in time, but in theory, when you're actually plucking the string, the magnetic field lines, because the flux is changing, it will go up and down and up and down, right? And because the direction of these currents are dependent on the direction of the magnetic field line, this means that if the magnetic field line is the opposite of what is right now, the current will also be opposite, right? So if it went down right now, it's going this way, or if it went up, it will go the other way, right? So let's find out how we can use that relationship to solve this problem. Okay, so what's amazing about this is that we can fix this issue of, also canceling out the guitar signal by simply switching the polarities of the magnets in the second pickup. Okay, just think about that for a little bit. Because guess what's going to happen? The direction of the current will switch to match the flow, right? Because previously it was flowing the green arrow was flowing this direction as well, right? It was going to collide with this purple arrow. But now that we switch the magnets polarity over here, if we use our right hand rule again, it's going to oppose the change, right? Oppose the change. So now they're going to all flow in one single direction. And that's pretty much the principle behind how this is going to work. Because if you remember again, electromagnetic interference has no relation to the magnets, right? Which means that simply switching the polarity of the magnets here is not going to affect the hums from getting canceled, right? Because the hums, the reason why they're getting canceled is because of the opposite wiring. It's not because of any things to do with a magnet, right? So that part is taken care of. So to look at it graphically, the hums, this is kind of all three graphs. So the hums are going to get met with kind of their counterpart that are going to cancel them out because of the opposite wiring. But you see that our signals are not going to get canceled because, again, we're going to switch the polarity of the magnet. And this diagram here, this third one over here, it's a little bit inaccurate because the amplitudes actually are not going to stay the same for the signal here. If you look at the flow here. They're actually all flowing in the same direction, right? So this means that the resultant wave is actually going to be double of what it would be from a single pickup, right? Because they're all flowing, it's going to be a sum, and that is why humbucker guitars are able to produce those loud and big sounds, right? Hopefully that really clears it up. And isn't that amazing? Because when I first learned this, it almost seemed a little bit too perfect to be true, since every factor just lined up so perfectly. Yeah, it's just so amazing. But to kind of just recap again, the opposite coiling is what cancels out the hum, and to preserve our guitar signal, we simply switch the polarity of one of the magnets, right? It doesn't have to be this one, it can be this one, as long as these two are opposite polarities. And there you have it. Oh, that is how we cancel out hum while preserving the guitar sound. So that about wraps it up for pickups. And now that we know how voltage is generated, it's time for us to really examine what comes next, right? Because although we did go pretty in-depth into pickups, they still are just the start of this whole cycle, right? They simply provide the electric voltage. So here we have a basic circuitry of an electric guitar, and just kind of look at it first. And I believe the best way for us to really tackle this problem of trying to figure out what's going on here is to first just examine the overall structure and then dive into the individual components. And there actually aren't that many examinations that we have to do here, other than the fact that I just want to focus specifically on the volume and tone components, right? So I'm sure we're all used to, especially if you're a guitar player, we're all used to viewing volume and tone as just these knobs, right? That we turn until we get what sound we want, and end of story. Well, what we're gonna do tonight is dig in a little bit further and really find out what is exactly turning the knob do, right? What exactly is happening in the circuit when we turn these knobs, and why is it happening? So I'm also aware that there's a particular symbol that we haven't really touched on, which are these arrows across these resistors, and these are actually called potentiometers, and they really are the start of the show here in these guitar circuits. So let's find out what they are and what they do first. So when you're turning any knob, okay, like a volume knob or a tone knob on your guitar, this is what you're turning, okay? It's called a potentiometer, and a good way to think about these things is to treat them as variable resistors, right? So you can think of it as a special type of resistor that can vary the amount of resistance, but a good way to start off is to still understand that this by itself is still a resistor, okay? And we can simply look at it visually that it contains 3 terminal points. We can call them A, B, and C. And the main function of this device is that terminal B here is connected to a wiper, right? And you can think of a wiper as just like another wire, right? Except it's adjustable. So when you turn the knob over here, you're actually turning the wiper. And just to note here that these are all interconnected, right? These 3 terminal points inside, they're still connected. It's just that terminal B, since it's connected to the wiper, it is adjustable. And that is what gives us the ability to adjust our resistance. And I know this is really hard to see right now since everything is covered up, so let's head over to the whiteboard and see what this means. Okay, so let's start off by drawing an inside view of the potentiometer. Okay, so oops. So it's gonna be like this, right? There's gonna be like a little inside path, kind of like this, right? Sorry about that. And okay, so hopefully it's not too confusing, but basically this is what the inside of potentiometer looks like. These are the 3 terminals again, so let me just label them A, B, and C, right? And again, B is the one with the wiper, right? This is what's adjustable. And we can, when you turn the knob, this is what's returning too. So it's also nice to visualize this because again, it's a resistor, right? So, which means we can kind of view it in the point of view of a resistor. So say if we just have like that, right? And this is point A, point B, point C, okay? And the main idea here is that the resistance, the total resistance from A to C must stay constant, okay? So let's say R of AC is equal to 500 kilo ohms. Sorry about that. 500 kilo ohms. So if A to B, let's say A to B is 200 kilo ohms, right? Well, since we know that A to C, the resistance must stay constant, we know that it must be whatever is left over, right? So if we already have 200 kilo ohms for A and B, A to B, excuse me, and the sum of A to B and B to C must equal A to C. So this means that B to C is going to equal to 300 kilo ohms, right? Because they have to add up to 500. Okay, and that's really one of the key ideas here. And so if we take a kind of point of view over here at the potentiometer itself, the same idea applies, right? So let's say we turn the knob about here, okay, and let's say this is 30%, right? 30% of the total resistance. That means, again, so if let's say A to C is 500, right? That means that the resistance from A to B is going to be 30% of 500, right? And whatever that is. And similarly, if this is 30%, it means the remainder is 70%. So that means that B to C is going to be 70% of 500 kilo ohms, right? And those two should add up to 500. And same thing if you do over here. So I hope you're starting to kind of see how the adjustments are kind of working here in terms of taking a fraction of the total resistance, because that's basically what this device is about, right? It's meant to be used as in how can we take just a tiny fraction of it when we need a certain amount. So now let's draw what we saw before on the circuit diagram, but only isolating the volume control. Okay, so remember we're going to have an AC current as our source, as our input source, because if you remember from our pickup, what we talked about in our pickup, because the voltages induced are in an oscillation, we're going to have an AC current. Okay, and that's the symbol we use to denote it. And let me just draw our little potentiometer real quick. So the way it's going to be set up is that you're going to have whatever this is going to be like your output source, right? So this can be like to the amp, right? Some wire to the amp. And the way it's going to be set up is that this is going to be connected to the ends over here, and we're going to have the wiper be here. Okay, so that means we can label this A, B, and C like before. And let's say our input voltage is 30 volts from the pickup. Okay, so based on what we just talked about, we know that if we turn the knob in a direction that, let's say, all the way over to A, okay, we would get the maximum volume. And that's because there will not be a voltage drop here, right? All 30 volts are going to go directly out into amplifier. So if we turn the knob so that the wiper is all the way directly over here, at A, we will get the full voltage, and that would mean that we're gonna get the maximum volume here, okay? Because the change in V is 0 at this point, okay? However, let's say we turn the knob towards C, okay, like that. Well, what's gonna happen is that we can also use the loop rule for this, but over here we're gonna have a change in voltage, right? There's gonna be a drop. So by the time it gets here, it's gonna be 0 volts. So this is the equivalent of basically muting your instrument, right? This is turning the volume all the way down so that because the voltage has to go through the resistance over here, there's gonna be 0 volts. That means nothing's gonna go out, okay? So like I said before, we can use the loop rule here, and how because it's 30 volts up this way, it's gonna have to be equivalent to the change, right? So it's gonna be negative 30 down this way, okay? And let's say we turn it anywhere in between these 2 points, right? Like there or there. Well, that's just gonna give us whatever fraction of that voltage is based on the position, right? And whatever that fraction is would then travel out to the voltage, out to the the amplifier. So if we were to think of this as like a knob, right? Turn all the way up would mean facing this way so that all the voltage is coming down, and if we turn it down so that the wiper faces point C over here, again the third terminal, we're not going to get any voltage, okay? And again, this is the same thing as what we talked about before, right? This whole idea of, you know, these 3 terminals and how they behave together, and how the sum of the resistances have to add up. Well, it's the same idea, except now we're going to be using it as a volume control, and that is how volume works. And hopefully that gives you a better idea now in terms of what is actually happening in the circuit when you're turning the volume. And we can now move on to tone. Okay, so tone works in a very similar way as volume, in that it also uses a potentiometer, except it's used in combination with a capacitor. And the reason for this is because the capacitor is going to be serving as a filter for frequencies, okay? So when we're turning our tone knobs and we hear kind of that very tight sound compared to like that more gloomy sound from the guitar, that's a change in frequency, okay? And that's what the tone is doing here. So let's first just draw the full circuit this time with both the volume and tone, so we can kind of see what's going on here, okay? So we're gonna have an AC current again, and for realistic purposes, let's have an R source, which is just to be the source of the resistance of the source. And if you remember, the tone is going to consist of this kind of resistor, which is also a potentiometer, with this capacitor, okay? And let's connect that, and we're going to have our little volume over here like we talked about before, and that's about it, right? So this is our overall circuit. And the best way to explain this kind of filtering process is by using scenarios with high and low frequencies, okay? And what I mean by that is, what would the circuit look like if the current was very high frequency versus low? Okay, so let's look at that. So let's start with higher frequency, okay? What would this look like? Well, again, we'll have the same power source, resistance, except now down the middle, it's not gonna have anything anymore, okay? It's just gonna flow straight down like that, and that's our volume, and this is our output source, okay? And let me explain the middle part right now. So what's basically happening is that over here, the capacitor is basically being charged up right now, okay? So when a capacitor is being charged up, you can think of it as it's just directly just going through it, right? There's very low impedance, and it can just directly flow through it, which means that the current is going to be really high. And when we have a high current, we can look over here at the source resistor, it means that there's going to be a greater drop in voltage, right, between these two positions. So because that this voltage droppage is big, it means that by the time we get all the way over here to the output, our output source is not going to get any voltage. Well, not any, but it's going to get a very low voltage. Okay, so V over here is very low. Okay, and again, this is because a lot of it was dropped from this resistor over here due to the overall high amount of current flowing through it. Okay, and that's because the capacitor is charging up. Okay, so let's see what would happen for a low frequency. So again, we're gonna have AC current, that, and this is our volume, and then output. Okay, so you see that I left it blank here, okay? And this is because at this stage in time, the capacitor is full, right? It's fully charged. And we know that when a capacitor is fully charged, there's not going to be any current coming through here anymore, right? It doesn't need anything. There aren't going to be any more movements of electron through this, right? So the current's going to be very low for the overall circuit. All right, and like we said before, that means that when we come over here to this voltage drop, because the current's very low, the voltage drop is going to be very low, right? Because there's not much current to begin with, right? So because the voltage drop is low, we can move over here and see what's going to happen. So when we come to the output, right, the voltage that we're going to feed into the output, therefore, is going to be very high, right? Voltage is high, and this is again because the droppage over here is low, which means the voltage coming over here is going to be high, and this is again due to kind of this disconnect over here that is because of the capacitor being fully charged. Okay, so we can also look at it in a more mathematical fashion. So let me just get some more room here. So if we were to look at it mathematically at the impedances at the from the capacitors, we know that impedance Z for each capacitor is 1 over 2 pi times the frequency and the capacitance. Okay, so by this equation itself, we know that if our frequency value here, right, F, if that's really high, we're going to get a very low impedance value, right? Because higher denominator makes overall value lower. And this is why more current is able to flow through, right? Because the impedance is very low. However, if we have a very high frequency, if we have a very low frequency, then it's going to make our impedance go up, all right? Because low or a small denominator makes overall value go up, and that's why there's less current, okay? Because the impedance value is higher now. So, and that is the basis for how tone control works. And hopefully both the math over here and the circuit diagrams gives you a nice idea about exactly what is happening by using these scenarios of low and high frequencies. And hopefully that will give you a nice idea now about what is actually going on when you turn those tone knobs, right? Alright, well, there you have it, guys. Those were the key physical concepts within the electric guitar. And to kind of help us gather our thoughts real quick before we leave, let's quickly just run through what we covered tonight. Alright, so we first got introduced to the pickup and how it was constructed and what kind of materials were used. Later on, we saw how any changes to the pickup's magnetic flux will ultimately induce an oscillating voltage, right? And this is due to Faraday's Law and kind of the principle behind why we even have electric signals to begin with. And then we kind of talked to a little bit on the side about humbucker pickups and how it uses clever coiling and polarity tricks to remove unwanted humming noises. Later on, we started talking about the electronics portion of the guitar circuitry, especially about an introduction to potentiometers and how they serve as variable resistors as well as controllers for volume and tone. And lastly, we ended off with how capacitors can be used as filters for frequencies. Alright? And my takeaway here is that, the next time you're trying to get rid of a humming noise coming out of your amp, or when you try to turn up the tone of your guitar, or when your neighbor yells at you to turn down the volume, hopefully during those times when you do those things, you will be able to now see this astounding physical aspect of what's really going on inside, right? And I hope that this presentation has helped you unlock a new scientific perspective at viewing these amazing instruments, and hopefully you'll develop your own curiosity to go down further in the future. And that's pretty much it for me. I hope this was enjoyable, and have a good one.